Hello everyone, in this video I will introduce you to our website and show you how it works. This platform is designed for plant disease detection. It plays an important role in modern agriculture by helping identify plant infection at an early stage. This allows farmers to protect their crops and avoid large-scale damage, leading to better productivity overall. Now we're going to walk through the complete deep learning part of the project. We will be using PyTorch, convolution neural networks, and a ResNet-style architecture to classify plant diseases from images. Here's a quick overview of what we will cover. You can find more details in the report attached. About the libraries, let's talk about what we are working with. The core of our stack is PyTorch, with torch.nn for building the network and TorchVision for dataset loading and transforms. We use PyTorch's data loader for efficient batching, with shuffle, multiple workers, and pinned memory for GPU transfer. For image I/O, we use PIL for visualization, Matplotlib, and Seaborn, and NumPy and Pandas for any numerical work. One important utility we define early on is getDefaultDevice and toDevice. These let us seamlessly move data to GPU when available, and this matters a lot. Training on CPU alone can take around 6 hours, while GPU bring that down dramatically. The Plant Village dataset has more than 87K images across 38 disease classes, split into 70K for training and 17K for validation. Image folder handles loading automatically using subfolder name as labels. Images are normalized to the 1 and 0 range, and our data loader uses a batch size of 32 with pinned memory for faster GPU transfers. Now, the heart of the project, the model architecture's CNN neural net. It's a ResNet-style architecture with residual connections. We start with a 3-channel 256 by 256 RGB input, then pass it through a series of convolutional blocks, 46, 128, 256, and 512 filters, with the batch normalization and ReLU activation. 2 residual blocks are inserted at the 128 channel and 512 channel stages. These skip connection and add the input directly to the block's output, which prevents vanishing gradients and lets the neural network learn identity mapping when needed. Finally, we flatten and pass through a linear layer that outputs 38 classes cores. The convolution block function makes the architecture modular and clean. Just pass in the channels and whether to pool. For training, we use the one-cycle learning rate policy with Adam Optimizer. 5 epochs, a maximum learning rate of about 0.01 weight decay. 1 times 10 to the negative 4, which equals to almost 0.0001. and gradient clipping at 0.15. The one-cycle policy annuals the learning rate from an initial value up to the maximum and then back down across all batches. This is the key to what's called superconvergence. We call sShed.step function after every single batch, not after each epoch, and the results speaks for themselves. At the baseline, our model is at just 2.77% accuracy. By epoch 1, it jumps to 77.5%. By epoch 2, it's at 88.6%. This is amazing. By epoch 3, it's already at 90.9%. And finally, by epoch 4, it hits the 98.23%. That's remarkable progress in just 4 epochs. Now looking at the training curves, the convergence is fast and clean. Validation loss collapsed from 3.64 down to 0.057, which tells us the model is generalizing well. It's not just memorizing and training data. The accuracy curve mirrors this, shooting up quickly and leveling off near to 98%. After training, we save the model using torch.save so it can be reloaded for inference and integration. And now we're going to continue with the walk through the website. We use artificial intelligence to instantly identify parasitic diseases and nutrient deficiencies. Our deep learning-based system ensures optimal scalability and accuracy. As you can see, this is the homepage of the website. It shows you our main feature, aka the analysis. The website is available in both French and English, making it accessible to a wider range of users. When you first click on the Start Analysis button, you are redirected to the login page. To access this feature, you need to sign in or create an account. You can log in easily using your Google account. As you can see here, we simply select an account and then the login is successful. Once logged in, you arrive at the main dashboard. Here, you can see the different sections of the website: the home page, the diagnosis page, and the history section. In the history section, you can view all the images that you have already analyzed. Now, if we log out, we can also sign in using an email and a password. If the email or the password is incorrect, the system will not allow access, ensuring security. As for new users, you can easily create an account by signing up, entering your email, choosing a password, and confirming it. Once that account is created, you can save your login information and access the platform. As you can see, with a new account, the history is empty. Now let's move to the main feature, image analysis. We select an image from our files and upload it. The system then processes the image. After a few seconds, the result appears. For example, here the model predicted that the leaf is a healthy blueberry leaf with the confidence of about 63%. The confidence here means the accuracy, and the processing time is just a few seconds. Let's try another example. We upload a different image and wait for the analysis. This time, the system detects tomato late blight with a very high confidence, around 99%, which shows the model's high accuracy for ill plants compared to healthy ones. Let me explain. Now let's see the model in action. On unseen test images, the prediction pipeline is straightforward. Load the image with image folder, unsqueeze it to add a batch dimension, move it to the device, run a forward pass through the model to get 38 class logits, then take the argmax with torchmax and decode the index back to a class name using the training dataset class lists. We tested this on several random images from the test set: tomato mosaic virus, apple black rot, corn common rust, and all the predictions were correct. The predict image function wraps this into a clean, reusable utility that we later integrated into the website so we can use. We can test another image. Here, the result shows a healthy apple leaf with a lower confidence, which indicates that these predictions may be less certain, as we discussed earlier. And now, if we go to check the history section, we can find all the previous analysis we did. This allows users to review the results anytime they want to keep track of their plans. Overall, this project shows how technology can support agriculture by reducing losses. We also designed this website to be simple and easy to use so that everyone, including senior users and people who are not familiar with technology, can access it without any difficulty. By making plant disease detection more accessible, this platform can help farmers and individuals make better decisions to protect their crops and contribute to a more sustainable and secure food system. And that's it. The full notebook covers everything we discussed today. If you have any questions about the architecture, the training setup, or how we extended this project, let us know in the next presentation, along with all your criticism and feedback. And thank you for watching.